we are going to work on the second half of this example. This is on page 336. So we have a 23 gram mass on a spring. So mass is 23 grams. Let's go ahead and convert that to kilograms. And the spring constant, K, is 46 newtons divided by meters. And we see that it's stretched to 12.3 centimeters. So let's convert the 12.3 centimeters to meters. So that's 0.123 meters. Then it's released. So we have to find our speed at 8 centimeters from the equilibrium. So if I was to draw out a graph of this again, we're starting off here at our 12.3 centimeters, or 0.123 meters. And that's where our potential energy is at max, and that's where the tension of the spring is exerting the maximum amount of force, and it's trying to pull this mass back towards the equilibrium of the spring. And then once it crosses over, the spring will be compressing and then pushing that mass back out. We start off here. This is where our 0.123 meters would be for our delta x. So for right there, this is our delta x. It's also the same as an A. And then here we have to find a point that's like 8 centimeters away from the equilibrium. In order to find the speed, we need to figure out what kinetic energy is, because that equation has the velocity component to it. But in order to find the kinetic energy, we are going to need to be able to find our potential energy and our total energy in the system. What we're going to end up needing to do is find our potential energy at 8 centimeters. Okay, so our potential energy equation, potential energy is equal to 1/2 of our spring constant times our delta x squared. Okay, and that's the same as our total energy at the max stretch. So nothing is converted yet. We're up here at the top of our amplitude. Let's plug in some more information here. So we've got our potential energy equals 1/2, and then our K, we already know the value is 46 Newton meters. 46 Newton meters. And then we can multiply by our change in x. So our stretch, our max stretch, is 0.123 meters. And then we have to square that. Okay, so that's at our amplitude, that's at our max stretch. So this gives us a total energy of 0.35 joules. Because at that point, the total energy in the system is only potential energy, and this is before we let it go. Okay, so we have to find our potential energy at a certain point along this pathway, and that's our 0.08 meters. Well, we know that total energy is equal to our potential energy plus our kinetic energy, and we already know that that is equal to 0.35 joules. Okay, so we can use our potential energy, try to figure out what it is at that position of 0.08 meters. Knowing the entire energy amount of the system, we can then use that to get our kinetic energy out of that. So if I was to find it, the potential energy at the 8 centimeters, I'm just using that as a subscript to kind of differentiate that so it's easy to tell it apart. We're not going to be multiplying that, it's just a label. So we've got our equation 1/2 times 46 Newton meters times 0.08 meters squared. Okay. 0.08 meters squared. Okay, so if I was to plug all this into my calculator, I would end up with a potential energy of 0.15 joules. So now that we know what the potential energy at that 0.8 centimeters, I can use that to find the kinetic energy. So setting it up in our equation here, our total energy is 0.35 joules is equal to our potential energy of 0.15 joules plus our unknown kinetic energy. So we can solve for our kinetic energy, and we end up with 0.20 joules is equal to our kinetic energy. Okay, so now that we know our kinetic energy, we can use this to find velocity. And why can we do that? Because the kinetic energy equation has velocity as one of the elements we multiply by. So kinetic energy equation equals 1/2 mv squared. So we already know quite a bit of this. We know what our kinetic energy is. 0.20 joules is equal to 1/2 times our mass, which was 0.023 kilograms, times our velocity squared, and that's what we're trying to figure out. We don't know what the velocity is. So if I was to simplify all of this, I would move everything over to the other side of the equal sign. 1/2 turns into 2 times 0.20 joules divided by 0.023 kilograms. Eraser. I'm going to do that. And I'm going to write it in red just so I can cancel some units. So a joule works out to be a kilogram times meter squared per second squared. Extend that out. Okay, so what can we cancel? Let's go back to the black. We can cancel our kilograms, and then we just end up with meters squared per second squared. And we're trying to find a velocity, but we still have v squared on the other side. Let me just work in my white space here. If I was to cancel everything out, I would see in my calculator it looks like 4.17 meters per second. And that's what I got by taking the square root of all of this and the square root of the meters squared per second squared. So that's how I got meters per second, by taking the square root of meters squared divided by second squared. And why I take a square root is because I'm trying to get rid of the exponent for the velocity. So that's how I ended up with that numerical value for just a plain old v. Okay? And you see I've got my 2 times 0.20 divided by 0.023. That's how I got my 4.17. I took the square root of all that. I end up needing a 2 sig fig number. Why would I need a 2 sig fig number? Well, I've got my 0.023 and I've got my 0.20. There's a division problem. So my 2 sig fig answer, 4.2 meters per second. And that is our velocity. So let's go back to our original slide. We started off with all of this. We needed to find our potential energy at 8 centimeters, or 0.08 meters. We did that. we found what our kinetic energy was at that point, and we used that kinetic energy of 0.20 joules to find our velocity at that point. 4.2 meters per second is equal to our velocity at 8 centimeters. If I was to draw this out larger in a waveform, see here you've got your max velocity, or speed in this case, right there when it crosses. You've got your max kinetic energy as well when it crosses. And then up here, we've got our max potential energy. And that's when the spring is totally stretched out. So for here, you've got your amplitude. Also, in this case, it's our delta x. That's from equilibrium to fully stretched out. So this is stretched on this side. And then this is compressed. And then the spring will just bounce. It'll just oscillate between being stretched and being compressed. It won't ever get any larger than this amplitude. That's the maximum limit that this is going to reach. Woo! And then over time, of course, it's going to dissipate. All the energy will head towards entropy, and it will stop moving altogether. But you'll see that there are different velocities at different points along here. So we found it here around the 8 centimeter mark. And then up here it was what, 12 point, let's see if I can find that again, 12.3 centimeters, yeah. So this is 12.3 centimeters, and we've converted all that to meters. So up here we had a lot of acceleration, we had a max acceleration, and then it starts to accelerate less as it approaches the equilibrium, and the spring isn't stretched out as much, it's not putting as much tension on there, so we've got max acceleration up here at the top as well. Max potential energy. Okay, so that's just a little graphical representation of how the spring works. You're going to want to be able to use these kinetic and potential energy equations. They're from Mod 7. So yeah, you're going to want to be able to calculate potential energy, calculate total energy, calculate kinetic energy at various points along the oscillation of the spring. And you're also going to want to know at what point is going to be the max velocity or the max kinetic energy, where all of your potential energy is converted. Now, you might ask, why are we at max kinetic energy here where we're crossing at equilibrium? And it's because you're hitting your max speed because all of the tension is being relieved, and all of the potential energy from here to here in the stretched direction has already been spent. And so then you've got your momentum that'll carry you into the compressed zone, okay? And that starts to add more potential energy back into the system as it slows down once the spring compresses completely, which would be at this amplitude here. So that'd be like your max compression.